So proving the fundamental theorem of calculus can be done rather rigorously or intuitively. I like showing students the intuitive way that Newton and Leibniz thought of it, as we try to make the connection between this discussion of area under a curve and antiderivative. Why should those two things be related in any way? So let's just take a look at this. We have a nice continuous function on the integral from a to b. We call it y equals f of x. And with regard to that function, we're going to try to accumulate some area. But before we do, let's get some notation straight first. Let's remind ourselves of what it means to take certain limits. For example, if you have the limit of delta y over delta x as delta x approaches 0, we commonly refer to that as the derivative, right? dy dx. Well, I'd like you to take that notion with you as you look at other types of limits that we'll be encountering in this discussion. For example, if you had the limit of delta a over delta t as delta t approach 0, that would just be, right, similar structure, that would just be dA dt. And as you'll see in a moment, we also want to look at the following. What if you had the limit as delta x approaches 0 of delta big F over delta x? Well, we would simply call that in Leibniz notation df dx. Okay, and we also could look at it in Lagrange notation. We could say this is the same thing as big F prime of x. This is the same thing as big A prime of t. And this is just, you could say, y prime of x if you want to, right? Y prime of x. Okay, so this notation that we have for derivatives is going to come in very handy as we try to analyze the area under the curve and the connection that it has with anti-differentiation. Why should those things be connected? And that connection between those things and differentiation, of course, is called the Fundamental Theorem of Calculus. So let's take a look at this function. If we wish to evaluate the area under a curve, y equals f of x, from, let's say, a certain value a that you see on the left, and if you have an integral that goes from a to b, we say, right, we're capturing the area under the curve from a to b. But what if you want to say, let's start from a on the left, and let's go to a certain value of x that's less than b, okay? So let's say we have a certain value of x right here, and it's clearly less than b, but we want to find the area that accumulates. We want to find the area that accumulates from a all the way to this x value, okay? Well, certainly if I put x there, I have a definite area. I have a certain amount of space that I've accumulated from a to x. And since that numerical value depends on the value of x, we could say that the area accumulated is dependent, or a function of x. It's dependent upon x, so it's a function of where I put that x value. So let's write down some familiar notation that captures what we mean by accumulating area up to a certain point. So let's see if I can erase this. This notation will come in handy later, but we don't really need it right now. Okay, so let's erase all of that. Okay. So if we want to capture, let's make an area function. We'll call it a net area function. The net area function from a to x can be written as a function, I'll call it big F of x, equals the integral from a to x of a little function, we'll call it f of t dt. Now you'll notice little f is something we've already used in this diagram. Little f is the function that we have in front of us, y equals f of x. But a lot of times students wonder, well, why in these textbooks they always use this, what's often called a dummy variable, which sounds quite insulting, but they use this other parameter t, right? They have this other parameter t. Why can't they just write the integral? We get this question a lot. Why doesn't the textbook say the integral from a to x of little f of x dx? What's the big deal? After all, it's the same function in the picture. Why should it matter? Well, if you think about it, looking at the picture on the left, once I choose x, I have a definite area. If I put x over here, I have another definite area, right? But once I choose x, think of it as kind of being fixed right there and saying, well, that's the area we want to accumulate. And if we're going to use a definite integral, right, if we look at definite integrals in this structure, meaning the area from a to x, we always said that the variable that we have in the integrand is going to vary between the lower limit of integration and the upper limit of integration, which in this case is x. So the reason why we don't put x in the integrand as well as in the upper limit of integration is because if you did, you would be saying, well, x is varying between a and itself, which doesn't really make sense. X is over here in the diagram. We don't mean to say that x is going to vary between a and itself. So we use another parameter, t, called a dummy variable, or just another parameter, an auxiliary variable, and we're going to let t vary between a and x. Just to keep in mind, just to be correct with regard to our diagram, okay? At the same time, however, I'll just erase this. At the same time, however, we need to keep in mind that depending upon where we put our x value will determine how much area we're going to accumulate. So it's appropriate to use x as a domain value for this big function f because the amount of area that's being accumulated is certainly dependent upon where I decide to put my x value. So there's a lot of things going on here conceptually that you just need to keep in mind. Okay? So we're going to refer to that as the net area function. And as mentioned, we're going to use a dummy variable t so we can avoid confusion with the x that appears in the upper limit of integration. Remember, please, that x is fixed once we choose it and cannot vary between a and itself. Now, what we're going to do is, for a continuous function that you see here, f of x, on this interval from a to b, as you see in this picture, we're going to add a little bit more to it. What if I said, well, I want to add another increment, if you will. And what if I call this location x plus delta x? Okay? I'm going a little bit past x to x plus delta x. And if I did that, clearly the amount of area that would be accumulated is now this much more. And since we're using the capital letter F to represent the net area under a curve, right, the net area that we're accumulating at a particular x value, if I go past this x value to another x value to the right called x plus delta x, I'm accumulating more area. So we could say that this space is the change, let me make that look a little better, is the change delta of f. This space right here is the change in the function f that results when I move my x value. Instead of stopping there, I go just a little bit more to this location, which I'm going to call x plus delta x. Okay, so that's going to be delta f. What we want to do now is approximate that delta f. Okay, and we're going to do that by using a rectangle. We're really good at using rectangles to approximate area, so we're going to use that same paradigm as we try to approximate the change in the area called delta f. So let's see. Let's build a rectangle. As we've done in the past, we need to choose a particular star value. Okay, so maybe I'll choose this x value right here, say. I have so many to choose from. But let me choose that as my x star value. That's a particular x value that I'm going to use now. I'm going to substitute it into the function, get a height, and I'm going to use this. Oh boy, my drawing skills are not too good right now. Let's see if we could do a little better than that. That's not too shabby. So I'm going to approximate the actual change delta f with the area of that rectangle. Okay, so we're going to approximate delta f with the area of that rectangle. So the reason why we love using rectangles is because finding their area is a very simple thing. Find the area of a rectangle, which is going to approximate delta f, so I should put not equal to, but approximately equal to. is simply height of that rectangle times the width of that rectangle. Now, since the function's name is little f, the height of that rectangle is simply little f of our star value, f of x star. And it's easy to see that the width of the rectangle is just the increment I went along the x-axis. We went here from x to x plus delta x, so clearly the width of that rectangle is simply delta x. Here we have an approximation for the change in area that occurred by moving x to x plus delta x. Now notice how I can alternatively write this. Oh, my deltas are not looking too good either. So let's see, delta f divided by delta x would therefore be approximately equal to f of x star, right? Since delta x is not equal to 0, I'm entitled to divide both sides of this approximation by delta x, and now I have this interesting expression which hopefully is starting to look familiar to you, right? So here's an interesting question. What does f of x star approach as delta x approaches 0? So that's an important question. Let's jot it down. Okay. As delta x gets really tiny, that is, it's approaching 0, what does f of x star start to approach? Well, it doesn't take much to look at the picture. If you make this rectangle here very, very skinny, if we get really, really, really close, right, when delta x is really, really, really tiny, then this f of x star is going to get closer and closer to simply f of x, giving us the answer to this question. So as delta x approaches 0, f of x star starts to approach f of x. Furthermore, when we say delta x approaches 0, we're really talking about taking a limit. So we can therefore say, well, if that's the case, the limit of delta f over delta x as delta x approaches 0, we just said is now going to equal little f of x. That's what it's going to approach. But now take a look at this expression and remember what we discussed in the opening comments. Isn't that something we recognize? Isn't that the derivative? The derivative of what? Well, that is simply, as Leibniz would write, d big F dx, or as Lagrange would write, big F prime of x equals little f of x. And there's the eureka moment that Newton and Leibniz had. This is how they intuitively got across to themselves, well, wait a second. It turns out that the derivative of the net area function, right, that's what we call big F, the net area function. The derivative of that net area function is simply equal to the upper boundary of the function at a particular location, right? If you stop at a particular x value, you accumulate an area. The rate of change of that area growing as you move past that x is equal to the value of the function little f of x at that same location. But this says something even more profound when you think about it. What it really tells us is that big F of x is an antiderivative of little f of x. So let me put that in red. That's an important comment. This says that big F of x is an antiderivative of little f of x. Okay? And since it's an antiderivative of little f of x, then we can make a very, very important statement. Okay? In fact, I'm going to have to erase some things in order to write this statement down. So let's see. I think we can erase up here and this discussion here. Since we've now extracted what we need from it, we're now going to run with this conclusion that we've made. Okay? So what we have been able to establish, right, is that a big F of x is simply an antiderivative of little f of x. That's what this statement here says. Okay? So when we look at it from a derivative perspective, whenever you want to write down big F prime of x, since f was defined as an integral, a function defined by an integral, that's nothing more than d dx of the integral from a to x of little f of t dt, which means we put that as little f of x. So that's why textbooks often say, well, you just replace the dummy variable t with the upper limit of integration x. But really, hopefully what you appreciate from this little discussion with the diagram is that what you're finding is the rate of change of the net area. And what this says is that the rate of change, the instantaneous rate of change of the area accumulated at a certain x value is equal to the value of the little function, little f, at that x value. Okay? Furthermore, since differentiation and integration undo one another, you could write this statement in another logically equivalent way, which is really cool. Check this out. You can say the integral from a to x of little f of t dt is equal to big F of x plus some constant c. Now when you think about that, look carefully. This statement says the same thing as this statement. Because if we differentiate both sides, right, if we differentiate or d dx, the integral from a to x of f of t dt, that's going to give us f of x, right? And if we differentiate the right side, that's simply going to give us big F prime, because the derivative of a constant is 0. So if you actually take a moment and think for a second, if I differentiate both sides of this equation, if I d dx on the left and I d dx this whole thing on the right, I would still have that same statement, namely that big F prime is equal to little f. Okay? This is one of the parts of the Fundamental Theorem of Calculus. And what I like to show students is that you can get the other part of the Fundamental Theorem of Calculus starting here. So let me just get myself a little more room here. And looking back at the picture, okay? The question is, how can we determine this value of c? We know we have what's often called the constant of integration, but we could do something really sneaky to find out how to express this constant of integration, which will lead to the other part of the Fundamental Theorem of Calculus. If we let x equal a, look at the diagram. If you start on the left at a, and you want to go all the way to x to accumulate area, but what if you let x be the same as a? That would mean you start at a, and you stop at a, which means you've accumulated 0 area. So if we let x equal a, something wonderful happens here. You would have the integral from a to a, right? Wherever I see x, I put a. The integral from a to a of f of t dt would equal, and again, wherever I see x, I put a, would equal f of a plus the constant c. But as we just concluded, if I start at a and I end at a, this definite integral, this accumulation of area must be 0. So 0 equals f of a plus c. And that's logically equivalent to saying, well, c equals negative big F of a. Make that look a little better. C equals negative f of a. And so if we go back to our statement from before, which is up top here, let's take a look for a moment. If we go back to our statement up here, if we go back to this piece right here, right? We now know that the integral, let me write this in black, the integral from a to x of f of t dt is equal to big F of x minus big F of a. Where did I get that from? Well, we used to say it's equal to big F of a plus c, but c is equal to negative f of a. And there you have the other part of the fundamental theorem of calculus. Most times textbooks will write it. They often call that part 1 of the fundamental theorem because it lends itself to evaluations, and most times textbooks deal with evaluations first. As long as the function little f is continuous, they'll say that the integral of little f of x dx from a to b is nothing more than an antiderivative, right? Big F of b minus big F of a. Okay? And as far as the other part of the fundamental theorem, what's often called in textbooks part 2 of the fundamental theorem, that statement is written exactly as you would see it in textbooks right up here. I just like to present part 2 first because I think it lends nicely to showing why part 1 is true as you do some neat tricks with the interval that you're on to accumulate area. So I hope that helps you get an intuitive understanding of the fundamental theorem of calculus so that when you're actually doing these problems, you know the significance of exactly what they mean. So we hope you enjoyed this video.